Hello, everyone, and welcome to Zero In. I'm Alistair Drennan, Content Director here at Innovation Zero. In this episode, I'm with James Walker, Chief Executive Officer of Nano Nuclear Energy, ahead of his participation in Innovation Zero 2024, to tell us about the company and its technologies, the wider industry, and what we can look forward to in the year ahead. So welcome, James. To start with, what inspired you to start the company?
Hi, Alistair. So thanks for having me today. Well, actually, the company didn't start as a nuclear company. It actually started with a group of individuals that wanted to be in the energy space because they saw that as being incredibly important for the future. But so a full analysis was done of all the technologies, and that included wind, solar, geothermal, even power transmission lines to move energy from one location to the other. But the reason why nuclear got settled on very quickly is that it was very clear that if you were analyzing the merits of each one, nuclear had more merits than the others. So it could be sited anywhere, unlike, say, wind or solar that needs good locational conditions, say good sun or good wind. It also had like the highest consistency of any power output. So it beats out gas or coal, which and that's really what held back a lot of the other renewables, is that the capacity factors of these things were very, very low. So you either built a plant that was 3-4 times what you actually needed with enormously expensive storage costs, or you went for this nuclear option, which meant you could put it anywhere. It would put out energy for as long as you needed it, and it was an exciting space because the whole nuclear industry was moving into the SMR microreactor technologies at this point. And so there was a lot of innovation in the space. You could see that the future was going to be nuclear and that the governments were going to go in this direction. And that's really why we started down on this nuclear journey. The reason why we went for microreactors, and just for your audience, the difference between a microreactor and an SMR is that anything beneath 20 megawatt output is considered a microreactor, whereas an SMR could be a small modular reactor, could be anything between, say, 20 megawatts and 400 megawatts. It could be huge. But we went for the microreactors because we believed this was the bigger potential business. Like if you had a very small reactor that fit with an ISO container that could be moved anywhere in the world, you could cater to mining sites, remote industrial projects, remote habitation, disaster relief areas, remote oil and gas, military bases, data centers, charging stations for EV vehicles. It was potentially an infinite market, and that's really why we started down this route.
And taking a look at the overall nuclear industry, what role do you see nuclear playing in the overall net zero energy transition?
So it's a good question, because at the COP28 that's just happened, there was a consensus that the world had to triple its usage of nuclear, and that's not just arbitrary. Like there are many examples of countries that have tried to move away from nuclear into other alternatives, and they've been hit badly because of it. So take Germany as an example. They shut down a lot of their nuclear power stations. They tried to move more towards, say, wind and solar, and the result actually was the fact that they could not power their country effectively. They ended up buying power from Poland that was produced by coal, and they ended up buying power from France that was nuclear. And so their costs of energy went up enormously, and so did their carbon footprint. And so it's not individual to them. The UK has been hit in similar ways when they've tried to branch off and do something other than nuclear. So it's essentially this decision that's come out to triple nuclear has come about because the alternatives have been exhausted now. And so there's big government spending programs that are coming out to promote nuclear, and that's the rebuilding of infrastructure and the expansion of it, and the promotion and support of SMR and microreactor companies, so that this new resurgence in nuclear can be accelerated as much as we can, because there's no way to get to zero without nuclear. Like we have tried, and we have these alternatives, but like nuclear is still the safest form of energy we've ever produced. Like if you look at deaths per gigawatt hour, it beats out wind and solar. It's very, very consistent, and it's zero carbon emitting. And ultimately, for the environmentalists, even they're beginning to support this now, because they see that this is going to have to be the solution. And unfortunately, like, physics is the way it is. You can't really amend the rules of the universe, and so that's really pushed us into a point where it's nuclear or gas or coal.
So as we move forward to this acceleration and expansion of nuclear, what do you see as being the key challenges facing the industry today? Is it funding? Is it planning? Is it public perception? Like, what's your diagnosis?
So I would say my background is actually as a nuclear physicist and nuclear engineer, and historically I would have said public perception was an issue because historically big nuclear projects were always part of the government, and so they never cared about PR for trying to make the public understand just how safe nuclear is. But to be honest, public sentiment has been improving so much that it's I think now it's got something like an 80% approval, which is historically some of the best it's ever been. And so obviously there's been a very good job done to sort of communicate the benefits of nuclear, combined with dissuading people from sort of more traditional concerns such as safety or radiation, things like that, which actually, when you're objective about these things, they're not issues at all. And so that's kind of gone away. I would say that I would reckon the biggest obstacle is the fact that the regulation around nuclear is an order of magnitude more intense than any other industry. And even for way more damaging and dangerous energies like coal or something like that, which kills, tens of thousands of times more people than nuclear could. The historic regulation framework is now being applied to the new generation of nuclear power plants, like the SMRs and microreactors. And it's not really a good fit, and there does need to be an overhaul of some of this regulatory framework to make it more compatible with new technologies. I would say if they can get that under control and make these amendments, a lot of the problems with deploying these devices will go away, and you'll be able to deploy them way more readily and inexpensively, actually, because unfortunately, like, nuclear should be one of the cheapest forms of energy in the world. Like, objectively, there's nothing more that compacts more energy into such a small space. But when you're going through that regulatory system, because it's so long and it's so onerous, that's years and years of capital expenditure, which then need big financing costs, which then increase the overall cost again. All of that could just go away, and the costs would come down so much more if you had a program that could analyze properly each reactor system and appropriately assign the regulatory framework for each one. So that I would say the regulations around nuclear would be the biggest obstacle.
So diving into your technologies, I suppose starting off with the transportability of it, why did you decide on a reactor designed, fitted to the dimensions for a truck?
So the reason why is that when we were looking at the whole business, so from start to finish, we thought, well, the reactor needs to be able to be shipped very easily, and like, we can't make this too large where we might have to disassemble it and move it into just separate trucks. What we want to do is make sure the whole reactor system is assembled and can be moved within one ISO container, because it's the least expensive option, and we have to be able to take advantage of the existing transportation infrastructure. So it needs to be able to go on the back of a truck, it needs to be able to go on the back of a train, and it needs to be able to go on a shipping vessel with the other ISO containers and be moved anywhere in the world. And the only way to ensure that transportability was to make sure that the reactor would fit within an ISO container, because that's the most widely distributed form of cargo in the world. So when we were starting off and we had our two technical teams, the MO that we gave them included that constraint. Obviously, if you weren't constrained by your dimensions, you could make a much more efficient reactor. But then again, you have the issue of disassembling it and having to assemble it at site, and that could be an enormously complicated thing. It could make getting it regulated and licensed much harder, and even for the end of life, it could make the whole process of disassembling it and decommissioning it and moving it away way more difficult. Whereas if we go through this sort of design selection criteria, at the end of life, we just take the fuel out of the reactor. The reactor can sit there for a year, and then we just move the reactor as one piece, and that's it. And so the liability of the entire thing can be removed from the customer incredibly quickly, and they don't need to even be concerned with it. We would take responsibility for that. So there were many good reasons for why we went for the ISO container route, but ultimately it was the ability to ship easily and quickly an energy source system for potential customers. And that was really the business driver behind it.
And how will the company scale up its operations to deliver so many reactors?
So the good part is that, say in the States, where our head office is, there are DOE loan programs, for instance, that are very interested in funding big projects like manufacturing projects like this. So the intention will be to not produce like 2, 3, 4, 10 of these things a year. It's to be produce hundreds. And because the designs are so simple, like we've had to simplify these things as much as humanly possible to make sure that they can be mass manufactured. We've actually got to a point now where we realize that these things can actually be 3D printed. And that could bring down the cost quite substantially, especially when you're producing hundreds of these things. So essentially, all we want is a nuclear battery on a truck with very few working parts that can just be shipped and plugged in anywhere we want. But that will bring down the cost quite considerably. There may even be a case where we have to sell the first few reactors at a bit of a loss, but that'll be like recouped incredibly quickly by the financial models indicate so, by that mass manufacturing and hopefully the 3D printing of these things, which you could not do with an SMR. They're too complicated and have too many working parts. But for a microreactor, which is very basic, you suddenly have that ability just to production line the whole thing. So.
Also, and how do you plan to ensure sufficient fuel for your reactors?
So it's a really excellent question, because a couple of years ago we wouldn't have had an answer for you, because when we analyzed the infrastructure, the nuclear infrastructure within the country, we realized that it essentially atrophied. Like the states, for instance, what they've been doing is just buying Russian weapons grade material and then downblending it to meet their domestic needs. But this meant that things like deconversion plants, enrichment plants, fuel fabrication, even the transportation of fuel, the infrastructure wasn't there. So we'd actually had not a panic exactly, but we saw that big companies like TerraPower had essentially decided to shut down their operation for a couple of years because they couldn't source fuel. And our solution was ultimately like, well, we don't know if we can rely on the Department of Energy to solve this issue. So why don't we actually just build out our own fuel fabrication facility with a deconversion component? And that way we can source enriched fuel and then convert it to the fuel form we want, and then fabricate it so it meets the dimensions of our reactor. And this actually opened up another business opportunity for us. So we've been working with the Department of Energy and the Idaho National Laboratory to put everything in place we need to start work on this facility. But that'll be it's another string to Nano's bow. So we hope that this facility will actually be up and running even before our microreactors are going. One, to obviously ensure we have our own fuel supply for our reactors, but two, this could be a really big revenue generating mechanism for the country, for the company, because this fuel is in demand, and at the moment it's a massive problem. So if we can get a hold of that, we de-risk our own operation and hopefully de-risk the company by adding that additional revenue to it.
Yeah, and speaking of risk, I suppose, how do you intend to deal with unstable global conditions that may impact uranium availability. Is that a concern for you?
It is a little bit because historically, say for instance, I think half the world's uranium at the moment comes out of Kazakhstan. And there's, to a certain extent, they have a good relationship with the US, but at the same time, currently what happens is that that uranium will go into Russia for enrichment. And in terms of energy sovereignty, the countries like the States or Canada, they're looking for their own energy sovereignty. And so that material supply is becoming increasingly important. So there are now funding opportunities to help with uranium production within the domestic country. And so and especially with the uranium price almost doubling, you're seeing a lot more investment going into uranium mining. I think for a start in Canada, as an example, they have some very big deposits that they're developing at the moment. And when they come online, obviously that's North America taken care of. I would also say that in Africa, they've got some very, very good uranium deposits that have been undeveloped. And with this big push into nuclear, especially the tripling, you'll see those deposits start to be developed into working mines. And so the global production of uranium will increase, but also the diversification of that source will increase too. Interestingly enough, I mean, Australia actually has big deposits of uranium, but they also have a ban on, I don't know if it's uranium mining, but it's certainly enrichment and nuclear power in general. So it's an odd thing where it could happen where Australia produce a lot of uranium that they can't do anything with, but it's very beneficial for the rest of the world because that can either go to France for enrichment or it can go to the States. And so I think it's very likely that certainly Canada, Africa, and Australia will become very, very big producers to try and meet this global demand, especially as we increase the nuclear power output in the world. So.
What industries are you looking to service with your reactor?
So originally when we first started, we thought actually one of the largest industries we could get involved here with is mining, because mines are very economically dependent on fuel. So mines are never in convenient places. They're never just next to a city. They're usually in very remote locations, especially big ones. And so that means the daily shipment of diesel, and enormous quantities of it to power that operation. And that can be the economic decider of whether that mine even gets commissioned or not. So we realized that one, you could actually provide nuclear power to a mine site, for instance, and it would actually be cheaper than the diesel itself, because the diesel suffers from that daily importation costs and all the associated logistics and personnel. Whereas nuclear power, you just put the reactor down and it just powers it for 20 years, and you can just leave it alone. It doesn't need any logistics or personnel, to bring in additional resources for that, to keep that thing running. So existing mining sites, but also if you have a microreactor like this, it immediately makes economic tens of thousands of mines that weren't previously economic. And so you can open up enormous amounts of resource wealth by having a facility like this. And we also realized that in Africa, for instance, where there are large sections of the continent which are off-grid, suddenly actually you could access enormous mineral wealth by having power systems in remote locations, while adding actually desalination capabilities, medical facilities that suddenly could have power. As soon as you introduce energy into these sort of locations, you can transform them completely. And there can be some questions that a lot of people have sometimes with regard to some countries' development. So even in South America, but a lot of the time it's to do with being able to supply consistent power to a region. And a lot of those regions might not have access to the grid power. Nuclear can change all of that, and suddenly you can have city anywhere you want. Really, it can be done, and that applies at the same time to like the big data centers that are being built, or the AI centers, very energy intensive. They also want to be outside the city in remote locations. Those things almost strictly have to run on diesel at the moment. Now, they don't want to run on diesel, and they don't want to. They want to meet their carbon emission targets, because otherwise you get penalized for it now. So even the tech companies are turning to nuclear as being the alternative that will give them a way to power themselves. And even Microsoft has put out funding opportunities for nuclear companies to submit requests of interest to be involved in the supply of these tech centers. So you're seeing it take off quite readily. I think as well, the other big one will be with the increasing amount of electrification of vehicles. The problem you will have is you cannot have just a charging station for an EV vehicle anywhere you want currently, because you either have to run it off a diesel generator, which defeats the whole point of it, or you need it to be powered by something like wind or solar. But the chances that you'll be able to have optimum conditions to be able to generate enough power to be able to power this remote charging station is very, very small. But a little microreactor could sit there for 20 years and just power hundreds of thousands of electric vehicles that come its way. So that'll very likely be a big business avenue in the future as well.
So interesting. The data centers thing is super interesting. It's something that we'll be talking a bit quite a lot at our event, because they use so much energy, like you say. Yeah, how will the reactors be manned?
So the good part is about these reactors is that, I mean, SMRs are very, very simple compared to the big civil power plants. And a microreactor is even more simple than an SMR. So really the operation of it on a day-to-day basis does not need anybody actually there. Now, obviously, somebody will need to be there for physical security and in case, I don't know, a tree falls on it or something and it just needs to be pushed off. But because it's such a simple device, we can actually have a central location where we monitor the behavior of all the reactors from a central location and can modify accordingly. And a reactor is a self-regulating system. So if it gets too hot, as an example, it produces more steam, more energy gets taken out, which means colder water gets put back in, which means the reactor then puts out less power going back. So it monitors itself. But the good part here is that we can have maybe 1 or 2 people on site just to physically intervene. They'll probably have very boring jobs and never do anything, but that's fine. And the central location where we monitor the behavior of all of these things. And that should bring down OPEX costs quite considerably, because we don't need a huge amount of personnel. They don't need to be physicists or engineers. They just basically need to be able to follow instructions from base. And if there is a need to shut down the reactor, that could be done from anywhere in the world. All you would just do is insert control rods, reduce reactivity, and it'll just sit there. And that's the end of it. So it's very likely we'll operate that sort of structure. We probably won't even sell the reactor to a customer. What's very likely is that they'll want power. So we'll just make them pay by megawatt. So dollars per megawatt over a certain amount of time, a contractual basis. So they avoid the capital costs of the purchase. And we'll just, and on our side, we'll recoup our own capital costs just through the selling of power over the contractual term. So that'll be just built into the cost.
And safety-wise, do your reactors share any safety or meltdown concerns with traditional large-scale power plants? And are there any new or different safety considerations that arise from your designs?
So the good part is that the big reactors, the worst accident scenario they can possibly have is, say they get a coolant leak. And the coolant leak leads to the reactor overheating, which leads to core melt. And then it's essentially damaged to the point where the reactor won't run properly again. And you're going to have not a cleanup operation exactly, but disassemble the reactor and separate the material. So, but that's the end of it. That's the end of that reactor. So with a microreactor, say every component was to simultaneously break, and the coolant was to leak out or something like that. The energy being generated is so small that it cannot lead to the core melt, which is the worst accident scenario. You actually just get a passive cooling effect. So even if you can't insert control rods to reduce reactivity, to put into standby. All that would happen is just the reactor would be hot, and nothing would melt, and it would just sit there until you could physically intervene. Worst case scenario, but so effectively you would just have a reactor that was warm. But the accident scenarios of core melt, things like that, they're not possible with this. Which is the real benefit, I think, of going very, very small as well, is that you have something that's fundamentally safe. Even if you were to effectively, I don't know, drive a plane into the reactor, all that would happen was that you would just have reactor pieces everywhere, and then you need to pick them up. But the accident scenarios are so much, they're so far fewer than for a big civil power plant, which is way more complicated and generates obviously way more power, and that can lead to that core melt. Effectively, you know, with our battery system, which is essentially what it is, like a nuclear battery, you'll never get close to having that kind of heat that would melt anything in the reactor.
So looking ahead to Innovation Zero 2024, a couple of questions. One, who are you hoping to meet, and what are you hoping to gain from the event? And then secondly, you'll be participating in a nuclear panel that we've got taking place. What are you hoping to share there? We've got like a sort of a key message for our audience that you would like to get across.
Well, I think one good thing from the conference will be we already have a big technical team in the UK that is building up our Uranium reactor, and ultimately what we want to do is get a concurrent licensing of our reactors going in the UK at the same time as the US. So there's going to be a big expansion into the UK, and what we ultimately want to do is start manufacturing there, get licensed there, and be able to distribute around Europe just using the UK as a base. So the advantage here is of these sort of conferences, one, it's connections to people. Find out who's in the industry, make connections to people that could be of enormous importance in the future. Find technical personnel, and just have these things on hand for when we do want to expand quite rapidly within the UK. And we're also just about to expand into a second SMR project too, and that might need additional personnel. So obviously meeting people, finding out who could be available or who could assist us, obviously all really good. And I would say the benefit of the panel is that it's very important still that messaging for nuclear is done properly and as widespread as we can, because there's still a large section of people who they'll have the same sort of concerns that you would typically expect, but these sort of panels are very good at dissuading them, because they can ask questions like, what happens if a terrorist gets hold of this thing, or is it safe, or what about the radiation? You know, things that actually have very easy answers to them. But it's just about putting those answers out there continuously so people are picking up on them, and we're trying to be part of that increasing public support that we're seeing for nuclear, and these sort of panels are really, you know, a good part of that. So yeah, the conference should be very beneficial for not just us, but like it's really the promotion of nuclear industry as a whole.
And a final question, I think you just touched upon it there, but any particular hopes and plans for the future? Any upcoming products or projects that you can?
Oh, we've got loads. I mean, 2024, I'd like to get the site sorted for the test bed, which is going to be the physical test work for the reactors now that the designs are complete. I'd like to make some real good progress with the design work for the deconversion and fuel fabrication facility. And there's some other technologies that we're buying at the moment from the National Laboratory System as well. And if I can just expedite that purchase to get going so we can develop those technologies more, we should have some additional products out from the company even sooner. And there's some 2024 will be a very big year for us. We have something very interesting happening around about February or March that I'm not allowed to talk about, but it should raise a significant amount of money for the company and allow us to increase our workforce personnel by hundreds of people. So it should be a very exciting year, very busy and probably very stressful, but it should be an exciting, good year. So
Great. Well, we really wish you all the best with that. And as I mentioned earlier, and as you just touched upon recently, you can see James at Innovation Zero 2024. He'll be speaking in our energy forum in our nuclear panel on day one, which is the 30th of April. You can also follow James on LinkedIn, James Walker, and take a look at Nano Nuclear Energy .com to find out more about what they're doing. So yeah, again, best of luck with everything that you're doing, and thanks so much again for speaking to us here at Zero In.
No problem, Alistair. Thanks very much for having me.
All right, take care.
You too. Bye.